Hello! So, in this video we're going to be talking about rational functions, and in particular we're going to be talking about horizontal asymptotes. So, horizontal asymptotes, there's sort of two pieces of this worth discussing. One, the first one I'm just going to talk about, which is that there's this misnomer that gets instilled a lot of the times, this mantra of you can't cross asymptotes. And that is blatantly untrue. In fact, horizontal asymptotes in particular, you can cross infinitely many times. Usually what that's sort of associated with, where that comes up, is the vertical asymptotes. And it's true you can't cross a vertical asymptote, but it's not because it's an asymptote, it's because it's a domain restriction, right? If you were going to sort of cross it, you would have to have a value along that vertical line, which, because it's a domain restriction, by definition you can't have that happen. So you can't cross vertical asymptotes, but that's only because they're domain restrictions. It has nothing to do with asymptotes. You can definitely cross, however, horizontal asymptotes. That being said, for rational functions, so horizontal asymptotes occur as a result that was some dysgraphia in action, as a result of relative growth rates. Now, growth rates is a phrase I've thrown around a couple times while talking about rational functions, because one of the main things to use for rational functions is use it to study relative growth rates. Unfortunately, the tool that you need to study growth rates are derivatives, and derivatives need limits, right? You're catching some repeating themes here. So once again, we don't have the proper analytic tools to really do this. Now, we can still do this in a sort of hand-wavy conceptual way, but this leads to a shortcut that students tend to sort of only remember the shortcut piece and not the reasoning, and that actively hurts people in calculus. So I want to make it very clear what's happening so that when you go into calculus, hopefully this part of calculus will be less confusing for you. So when we talk about growth rates, it is more or less what it sounds like. We're talking about how fast things grow, okay? So if we're looking at r of x as a rational function being some f of x divided by g of x, there's really three possibilities. The growth rate, I'm just going to abbreviate GR, of f of x is bigger than the growth rate of g of x. That's one possibility. The growth rate of f of x, the top, f of x, wow. My writing is going a little downhill, sorry, is less than the growth rate of g of x. So, first one, either the top is growing faster than the bottom, or the top is growing slower than the bottom. And the third option is the growth rate of f of x is about, which is what this symbol means, the little tilde, the growth rate of g of x. We can't really say equals, because equals is sort of a strong idea, which we actually mentioned back when we talked about equal signs at the beginning of the semester. So it's not that they're equal growth rates, it's that they're about the same. They're growing at roughly the same speed, not necessarily exactly the same speed. Now, these three situations dictate three different behaviors. So, in the first case, if f of x is growing much faster, or growing faster than g of x, there is no horizontal asymptote. okay? In the second case, so this is because, so a horizontal asymptote, if you remember when we talked about asymptotes way back, horizontal asymptotes are this end-term behavior idea. And if the top function is growing much faster than the bottom function, then there's sort of nothing stopping it from just growing out of control. And so it just goes sort of up, up, and away, right? Like polynomials do with positive leading coefficient, or exponentials do, again, with positive leading coefficient. So there's no sort of ceiling that it sort of bumps and starts trying to sort of bend toward. So there's no horizontal asymptote. Now, if the growth rate of the bottom of the top is smaller than the growth rate of the bottom, much slower growth rate, and the bottom is getting big really quick compared to the top, that means, that means that you are dividing by a much larger number, which means your overall thing is getting sort of crunched down because you're dividing it by some larger and larger number compared to the top. And so this means that you have some horizontal asymptote, and specifically, the horizontal asymptote is 0. So in equation form, you'd say y equals 0. And this is because, essentially, the bottom is growing fast enough that it's just crushing everything back down to being some very small number because you're dividing by a much larger number, right? So it gets small. Now, if the growth rates are about the same, then a horizontal asymptote exists and is a ratio of the rates. So I'm gonna put sort of quotes around this, a ratio of the rates, because this is really a part that you definitely need calculus for to make sense of, and we don't have that. Nonetheless, this explanation will get you through sort of the conceptual level, will get you through horizontal asymptotes, even in calculus. Because this is the sort of right way of thinking about this, is that you really want to think of it as growth rate on the top versus growth rate on the bottom. The problem is that we don't have a good notion of growth rates without limits, and we don't have limits. There's one exception to that, though, and we've already talked about it, which is that when we talked about polynomials, we talked about this idea of a leading term, and how the term with the highest power is sort of growing faster than all the other smaller powers. And that's why it sort of dominates eventually, and we get this eventually it acts like that sort of leading term, monomial, and the other things sort of fade away and don't matter eventually, right, for big enough. Well, that's exactly the situation we're talking about here when we're talking about growth rates. And so this is the part where people tend to sort of jump ahead, and the part that I'm trying to suggest you don't necessarily jump ahead. So in particular, for f and g polynomials, we actually do know things about growth rates because the growth rate is represented by the degree of the leading term. So for f and g, essentially it's the highest power wins argument. So for example, because concrete examples are helpful, let's say r of x is 3x squared plus 2x minus 1 over 6x cubed plus 2x minus 1. Okay? In fact, let me make it plus 1, just so they're not quite exactly the same. So the argument here is the growth rate for a polynomial is essentially dominated by that leading term. So here at the top, the f piece has a growth rate equivalent to some x squared. The bottom is some x cubed, right? X cubed wins, it's a bigger power. And so that tells you that the growth rate of g, the bottom, is the bigger thing compared to the growth rate of the top, of the f. And so it's this situation, right? The bigger power is on the bottom, dominating the power on the top, and so it has a horizontal asymptote of y equals 0. And it's really that easy. But again, I want to sort of stress that we're using polynomials here because they are the things that we have a mechanism to talk about growth rates for. But if you when you go into calculus, you'll have much more powerful tools at your disposal to discuss growth rates. And so this rule of looking at powers is going to become quickly irrelevant. So this idea of highest power wins is not going to actually help you very long. It's what we need in this class, but in the next class, it's this piece, right? This idea is what you need in calculus, less so this idea, okay? Nonetheless, this is sort of a useful thing to use to remember this if you need to. So let's do another example. So let's look at, let's say, h of x. Let's do 3x to the 6th plus 1 over 2x to the 6th plus 3x to the 5th plus 2x squared plus 1. Okay. Let me rewrite that because that's terrible looking. That's better. Oh boy. All right, so this was x to the 6th plus. Okay. So again, we look at this and this highest power wins argument, right? So what we want to look at is growth rate at the top versus growth rate at the bottom. But now, highest power wins, so I have 3x to the 6th on the top, 2x to the 6th on the bottom. I have other terms. You might think that they would sort of make a difference because they're much bigger than just 1, right? So this is definitely getting bigger. But again, no, because the highest power eventually just outright dominates the others, and they don't matter eventually. In the short term, they definitely do matter. And in the short term, this thing will be bigger strictly sort of because of that reasoning. But we don't care about the short term, we care about the long term. That's what the horizontal asymptotes are for, is this end-term behavior. And eventually, the x to the 6th term is going to be so big that this stuff is going to be negligible next to that. And so, since they have the same power, neither is winning. It's not the case that the top is much bigger than the bottom. It's not the case that the bottom is much bigger than the top from a growth rate, because the growth rate is x to the 6th, right? So the growth rate is about the same, which means now we're going to look at a ratio of those rates. And for polynomials, what that means is that we're going to look at a ratio of the leading coefficients. So the horizontal asymptote occurs at, so I'm going to write it out sort of the long way, 3x to the 6th over 2x to the 6th. But obviously the whole point was that they're both x to the 6th. They're both going to cancel out. So really what I get is a ratio of the leading coefficients. But I want to make it clear that it's not that the leading coefficients are the thing I care about so much as it's the whole term. It just happens that because they are both x to the 6th, they cancel out, which is why I get down to the leading coefficients, okay? And specifically it's y equals this. So my horizontal asymptote is y equals 3/2. Okay? So this is, again, this is horizontal asymptotes at this level, at pre-calc. But you do a lot more in calculus because you get limits and derivatives, and those are sort of key things to study growth rates, and that's exactly what's happening here. So this sort of bit about the highest power is important, and this is what you'll need to know for exams and quizzes and things in pre-calc, but it's really this idea that you need for calculus. So it's better to sort of remember this and then remember that the highest power wins and sort of fit into this rubric, rather than just skipping to looking at just powers and knowing things about polynomials, because that is sort of very deliberately not helpful in Calc 1, where you're going to do this a lot. Okay? So that is that.